Hi everyone, so this PowerPoint is to introduce to you the idea of using radians as an alternative measure for an angle. But to start off with, just a recap from way back when we did GCSE, can you find the area and circumference of the circle with a diameter of 10? And then in the second question, I want to find the area of the sector AOB and the length of the arc from A to B. So pause the PowerPoint now and have a go at those two, and then on the next slide I'll go through the answers. So now I'm going to go through the answers. Question 1, we're looking for the area of the circle, so there's a formula, remember, that is pi r squared. So for this question you have to do pi times 5 squared, because the radius is 5, so that's 25 pi. Sometimes you can leave your answer in terms of pi, or if you type that into your calculator, it's just over 78, it's about 78.5, and then I'm going to put centimetres squared. For the circumference, we're doing pi times diameter, pi d. So for this question, it's pi times 10. So if you want to leave it in terms of pi, you can write 10 pi, or 10 times pi off your calculator is approximately 31.4, and that's measured in centimetres. For question 2, to find the area of the sector, this sector is part of the circle, but it's not the whole circle, it's just a fraction of the circle. Now the fraction of the circle that it is 32 out of 360, because it's only 30 degrees of the full circle, which is 360, and it's that fraction of the area of the whole circle. Well, the area of the whole circle will be pi r squared. Now this circle is actually the same as the first circle in question 1, because it has a radius of 5. So I'm going to do 32 out of 360 times pi times 5 squared. So on the calculator, 32 out of 360 times by pi times by 5 squared. You can leave it in terms of pi if you want to, it's 20 over 9 pi, or as a decimal it would be about 6.98 or 7.0 if you want to do one decimal place. And then the arc length from A to B, again it's part of the circumference, but it's not the whole circumference, it's just a fraction of the circumference, and it's the same fraction as earlier, 32 out of 360. So I'm going to do 32 out of 360 times pi times the diameter, which would be 10. And from the calculator, that's about 2.8 or 2.79. And that was going to be measured in centimetres because it's the length of an arc. Okay, so let me introduce to you then what a radian is. When you're measuring angles, up until now you've probably just used degrees to measure angles, but there are other units that can be used for measuring angles, and the one that you need to know about now is radians. And radian measure is essential in higher level mathematics. So radians are very often used in more difficult mathematics. So for example at university, or if you go on to do a mathematical job, you might find that you're using radians quite often. So let me define to you what a radian is, so just one single radian. So if you look at the picture here, I've drawn a sector into the circle, and I've labelled the radii with the letter R. So you've got a radii here, which is length of R, and then another radius, I should say, another radius there. Now if we open up that angle to the perfect size so that this arc length is also exactly the same as R, then we have created what's called 1 radian. So an arc of length R on a circle with a radius of R subtends an angle of 1 radian. So maybe now you can have a look at the picture and guess roughly how many degrees you think that is. We'll look later on at exactly how many degrees it is, but it's an acute angle. That's the size of 1 radian. When you're measuring in degrees, we usually put that little 0, a little O, after the number. For radians, the symbol is a letter C, or sometimes you see rad for short. Okay, so in this picture again, we've got 1 radian as the angle because the arc length is the same as the radius. So in this case, we could write this little formula down. The arc length is equal to the radius multiplied by the angle, because the arc length is R And if we do radius times angle, that would be r times 1, which is also r. Now imagine that we increased the size of the arc to make a full circle. So imagine those two lines, which I'm now going to colour in red. Imagine we opened those lines up so that the angle got bigger and bigger and bigger, and the arc length around there got bigger and bigger and bigger. So it's not 1 radian anymore. So we're increasing the size of the angle. And imagine we made that arc length go all the way around a full circle. So if we did that, the arc length would be 2 pi r. That's just a formula for the circumference, also known as pi times diameter, isn't it? But the diameter is the same as 2 radii, so this is the same as 2 pi r. So if that angle got made so big that the arc length went all the way around, then the arc length would be the full circumference, which is 2 pi r. But what we want to work out now is what would the angle be? Well, going back to that formula from earlier, the arc length is equal to the radius times the angle. If we increase the arc length to make a full circumference, so the arc length is now 2 pi r, the radius of the circle hasn't changed, so that's still r, which must mean that the angle must be 2 pi. Because what have we got to multiply r by to get 2 pi r? It's 2 pi. So the angle then must be 2 pi. So therefore, if we open that angle up so big that it becomes a full circle, the angle in radians is 2 pi. So this is a fact that you need to memorise. A full circle, which you were used to calling 360, if you measure in radians, is 2 pi radians. And remember that little C symbol means radians. So that's a fact that you now need to memorise. So we could practice converting between radians and degrees. So I would press pause now to fill in that table and to see if you can convert these angles from radians into degrees. You'll notice that angles in radians are often written in terms of pi. So for example, a full circle is 2 pi radians, which is 360 if we're measuring in degrees. So press pause now before I reveal the answers and see if you can fill in some more of these. So I'm going to reveal the answers now. Press pause if you haven't tried them already. So full circle is 360 degrees, which is 2 pi radians. If we half that and we just go through pi radians, that's half of the circle, which is 180. If we divide by 2 again, pi over 2, that's the same as 90 degrees. So this is a right angle. In radians, it's pi over 2. If we half it again, we get 45 degrees. And if we half it again, we get 22.5 degrees. 1 radian, if we wanted to get, for example, from that line to that line, if we wanted to turn 2 pi into 1, we could divide by 2 pi. We'd have to do the same thing then with the degrees. So if we divide both of those by 2 pi, we get 1 on the left and 360 over 2 pi on the right. And then that can be simplified because 360 divided by 2 is the same as 180. So 1 radian is the same as 180 divided by pi. So on the calculator, if I type in 180 divided by pi, I get about 57.3, I've rounded there to 1 decimal place. So 1 radian is the same as 57.3 degrees. So if you look back to that picture from earlier, the one where I said have a guess how many degrees you think it might be, the answer I was looking for there was 57.3, so that's what 1 radian is in degrees. And then these are the answers on the right hand side. If you divide pi by 6, you get 30. If you divide pi by 5, you get 36, etc. 1 degree is the same as pi over 180 radians. So these are the main facts. This is a really good one to memorise, half of a circle. In degrees it's 180, but in radians it's pi. And if you want to convert between radians and pi, it's all about timesing or dividing by this fraction, 180 over pi, pi over 180. So we'll have a look at some more examples in a minute of converting between them. Before we do that though, your calculator has a radian mode, and in your exam you might need to change between degree mode and radian mode quite frequently, so you need to make sure you know how to do that. You've probably got your calculator in degree mode at the moment, because that's the mode you would have been using up to now. So you can probably see a little letter D on the top of your calculator, D for degrees. If your question's in radians, you need to change that into the letter R. So on the Class Whiz calculator, if you press Shift and then Menu, you'll see that number 2 is the angle unit. And if you click number 2, the angle unit, you get 3 different options. Number 1 is degrees, number 2 is radian, and number 3 is gradient. We're going to ignore number 3. We're just going to focus on 1 and 2, which are the degree and the radian. So you need to make sure that on your calculator, you know how to change between degree and radian mode, because you're going to have to do that frequently throughout your exam. So here are a couple of examples from the booklet. Just going to check what page they're on. They are on page 2. Convert the following angles into degrees. So we've got 7 pi over 8 radians. Very often radian angles are given in terms of pi, and we want to change it into degrees. So the way to do that is to multiply the angle that you've got in radians by 180 over pi. So you can see in part A, multiplying by 180. They've also divided by pi. Pi has disappeared. So to get from radians into degrees, you multiply by 180 over pi. So you can have a look through those 2 examples on your own. And then here's another example. This is going the other way. This one's going from degrees into radians. So the method they're using here is multiplying by pi over 180. So it's just the reciprocal of the last slide. So you can get from degrees into radians by timesing by pi over 180. So in your booklet on page 2, there's an exercise there, exercise 1. Question 1, converted these angles from radians to degrees. Question 2, use your calculators to convert from degrees, to degrees, so you're going from radians into degrees. And then question 3, all they want you to do is to type those into the calculator, so sine of 0.5 and press equals. The point of question 3, I think, is to check that you can get your calculator into the right mode. So have a go now at sum of 1, 2 and 3. So next I'm going to move on then to some formulas. We're going to go back to what we looked at in the starter, which is the arc length and the area of the sector. And we're going to convert our method now from degrees into radians. So this is the way that we did our starter question for the arc length. So when you're finding the arc length, it's a fraction out of the full circle times by the circumference. And remember that 2 pi r is just a formula for the circumference. It's the same as pi times diameter, but 2 radii are the same as the diameter. So that's the formula that we were using earlier. That's if you're measuring in degrees. But if we now change this into radians, the formula will change a little bit. If we're working in radians, then our angle, instead of dividing it by 360, we would divide it by 2 pi. Because remember, a full circle is 2 pi radians. And we'd multiply it by 2 pi r, that's our circumference. And then you've probably spotted that this formula will simplify, because there's a 2 pi on the top and a 2 pi on the bottom, which will cancel each other out. So if we cancel those, the only things that are left are the angle and the radius. So our arc length formula is r theta, radius times angle. So you can see that that formula becomes really straightforward and easy when you're working in radians. Let's do the same thing now with the area formula. So if you were measuring in degrees, you would do your angle out of 360 times pi r squared, so that's the area of the sector. But if we were going to change this to radians, then our area formula instead of 360 degrees, we'd write 2 pi radians times by pi r squared. Now this time the pi on the top and the bottom will cancel. Nothing else will cancel. So on the top we've got an r squared and a theta. And on the bottom we've still got that 2. So here's our formula for the area of the sector. R squared theta over 2. So those formulas are much simpler when you're working in radians, but remember those ones that I've coloured in yellow, they only work if you're measuring in radians. So here they are again, these are the formulas to learn. They're not given to you in the formula booklet, so you do need to memorise them. Arc length is r theta, and area of sector is r squared theta over 2. So let's have a look at an example then of putting that into practice. In this picture, the arc AB subtends an angle of pi over 3 at the centre. So I can tell that this question is a radians question because the angle is given in terms of pi. The radius of the circle is 6 centimetres. Find the length of the arc AB and the area of the sector OAB. So the arc length, using our formula from earlier, is just r theta, radius times angle. So for this question, that's just 6 times pi over 3, which can be simplified into 2 pi. You can leave your answer as 2 pi if you want to. It depends whether it asks you for a decimal or not. But I'm quite happy to leave that in terms of pi. It's a bit more accurate than a rounded decimal. The area of the sector, the formula was r squared theta over 2. So for this question, that's 6 squared times by pi over 3 over 2. Well, 6 squared is 36, and 36 over 3 is 12, so that's 12 pi over 2, or if we simplify even further, it becomes 6 pi. Again, I'm going to leave my answer in terms of pi. I'm just going to add in my units. Area would be centimetres squared, arc length would be centimetres. So they're very easy formulas to use. So there's an exercise now, which I think is on page 7 of your booklet. We've got some pictures, some circles. I would work out the area and the arc length. It only says to find the area of the shaded bit in the booklet, but I would do the area and the arc length just to practice both of those. So have a go now at perhaps A, B and C on page 7. So now I'm going to go through this exam question. It's quite an old question, but still a really good one. And what they've done here is they've given us a diagram, points P and Q on the circle, the centre is O, and they tell us that the radius is R and the angle POQ is theta radians. They tell us that the length of the arc from P to Q is 6 centimetres, that arc length around there, 6 centimetres, and then the area of the sector, which I'll just colour in now in yellow, the area of that sector is 22.5. And they're asking us to find the values of r and theta. So they've turned the question on its head really, because using our formulas from earlier, we were told r and theta and we worked out the arc length and the area. Now it's backwards. They've given us the arc length and the area and they're asking us to find the radius and the angle. So it's backwards. And that's what they tend to do on this topic to make it a bit more tricky, because the formulas, I'll just write them down at the top here, the formulas are very easy to use going forwards. So to make it more difficult, they give you the answers and ask you to work back to find the radius and the angle. So let's get started. I'm going to write down the formulas with everything I know substituted in. So I know the arc length is 6. So from the top one I could say 6 equals r theta. And I also know the area of the sector is 22.5. And that equals r squared theta over 2. They're asking me to find two things, which straight away is making me think of simultaneous equations. I've got my two equations, I've just written them both down, so now all I've got to do is solve them as simultaneous equations, and I'll be able to work out r and theta. Now before I start solving them, I think that second equation I should times both sides by 2, just to make it look a little bit nicer. So if I times both sides by 2, I'm going to get 45 equals r squared theta. Now that second equation looks a little bit nicer, so I've got equation 1, I've got equation 2. Now there's lots of different ways of solving this. You could divide the equations. I think that's probably the best way of solving this one. So I could do equation 2 divided by equation 1. Now if I do that, I'm going to have 45 equals r squared theta, and then I'm going to divide it by 6 and r theta. Now the reason that that works out so nicely is because when I divide them, the thetas are going to cancel each other out, and then the r on the bottom will cancel one of the r's from the top. So 45 over 6 equals r. And that can be cancelled down. 45 divided by 6 is 7.5. So I now know that the radius is 7.5. All I've got to do now is work out theta. So if I sub this into one of the equations, I'm going to choose equation number 1. So I know that 6 equals 7.5 theta. So theta then is going to equal 6 divided by 7.5, which is 0.8 or 4/5. And I'm going to put the little c to show that I'm measuring in radians. So that's a useful trick to remember there about dividing the equations. It's a great way of getting letters to cancel out. And there's my final two answers.